Welcome to Night Lesson. Relax and learn along the way. Intro: The Revolution in the Mind. Imagine a young man sitting in a quiet office in Bern, surrounded by the soft rustle of paper and the steady ticking of wall clocks. His job is to examine the inventions of others, to understand their mechanics, to assess their logic. An unassuming civil servant, whose daily life consists of patterns and patents. But while his hands sort through drawings of gears and levers, quiet revolutions are taking place in his own mind. In the calm of this office, hidden from the world, thoughts are forming that will shake the very foundations of our understanding of time, space, and the nature of light. Who would have thought that within this humble dreamer slumbered one of the greatest thinkers of all time? At the end of the 19th century, the world of physics seemed almost complete. The universe was like a magnificent clockwork, whose laws, described by Isaac Newton, appeared to explain everything. Yet, on the horizon, fine, small clouds were gathering, unsolved puzzles about the nature of light and the mysterious forces of electricity. It was these small inconsistencies, these quiet whispers at the edge of the known, that would not let the young man in the patent office go, sending his mind on a journey. What follows is a gentle journey through the life and the thought worlds of this giant of the mind. We will trace his childhood questions of wonder and explore the lines of thought that led him to his groundbreaking theories. Simply lean back, breathe deeply and evenly, and let us together immerse ourselves in the fascinating world of Albert Einstein. Let the thoughts of the day slowly fade, as we set out to rediscover the universe through his eyes. Chapter 1. What might be going on in the mind of a little boy who, lying sick in bed, holds a small, unassuming device in his hands for the first time? Our journey into the mind of Albert Einstein begins not in a laboratory or a lecture hall, but in a quiet child's room in Munich, around the year 1884, shortly after his father had given him a small compass. 5 years earlier, in March 1879, he had been born in the Danube city of Ulm, into a middle-class Jewish family that soon moved to the Bavarian metropolis. But it is this one moment, this instant of stillness and contemplation, that ignited a spark that would burn for a lifetime. His father had brought him a simple pocket compass to cheer him up, a small, round casing of brass, cool and smooth in his child's hand. Beneath the protective glass lay a needle, trembling restlessly, as if it were listening to something no one else could hear. Albert turned the case, moved it back and forth, but the needle seemed to have a will of its own. No matter how he oriented it, it swung steadfastly back, always aligning itself with the same invisible point to the north. For the child, this was pure magic. There were no threads, no hidden mechanisms, no visible hand guiding this needle. And yet, it moved with an unshakable persistence. In that moment, he felt for the first time the presence of a hidden order, a force that permeated the empty space around him. It was his first encounter with the idea of a field, an invisible structure that mysteriously influences matter. The question that formed in his young mind was simple, yet profound. What was this invisible force? Why did the needle do what it did? This question never left him. It was the seed from which his monumental theories about the fundamental forces of the universe would later grow. This inner world of wonder and deep curiosity stood in stark contrast to the outer world that surrounded him. His school days at the Luitpold Gymnasium in Munich were marked by a deep aversion to the rigid, Prussian-style education system. The focus here was not on understanding, but on memorization, not on questioning, but on obeying. The mechanical drill and the blind authority of the teachers stifled his natural thirst for knowledge. He was considered a daydreamer, a slow learner, someone who refused the simple rules. While his classmates recited facts, his mind would wander to faraway places. He imagined what it would be like to ride on a beam of light. What would the world look like from that perspective? These were early, subconscious thought experiments that already contained the essence of his later theory of relativity. His real learning took place not in the classroom, but at home. The Einstein household was a place of intellectual stimulation. His uncle Jacob, an engineer, brought him books on algebra and geometry, which Albert devoured. He found a deep beauty and elegance in the clear logic of mathematics, which school had presented to him as so dry and lifeless. And then there was music. Playing the violin became his sanctuary. In the harmonies of Mozart and Bach, he found another kind of structure, a universal language that brought comfort and order to a chaotic world. When his family moved to Italy for business reasons, the young Albert initially remained behind in Munich to finish his schooling. But the separation from his family and the growing contempt for the oppressive atmosphere of the gymnasium became unbearable. He felt trapped, his mind imprisoned in a system that did not understand him. Finally, at the age of 15, he made a bold decision. He left school without a diploma, followed his family across the Alps, and entered a time of freedom and self-discovery. In the warm, vibrant culture of Italy, far from the strictness and the drill, his mind could finally breathe. He wandered through the landscapes, read, thought, and solidified his resolve to understand the world in his own way, guided not by teachers, but by the unshakable curiosity that a small, trembling compass needle had once awakened in him. Chapter 2. The path that led from the freedom of the Italian Alps was not a straight one. After graduating from the Zurich Polytechnic in 1900, the young Albert Einstein found himself in a world that had little room for his particular way of thinking. Academic positions were denied to him. His applications were ignored or rejected. The need to earn a living for himself, and soon for his small family, pushed him from the lofty heights of pure theory down into the pragmatic reality of everyday life. After 2 years of uncertainty and minor jobs, he finally found an anchor, a position as a technical expert, third class, at the Swiss Federal Office for Intellectual Property in Bern. One might imagine this place as a dead end, a quiet siding for a mind destined to traverse the universe. But the Bern Patent Office became something unexpected for Einstein, his own personal thought workshop. His desk, laden with the applications and sketches of inventors, was not a prison, but a window into the applied physics of his time. Day after day, he pored over plans for electrotechnical devices, for mechanisms to transmit signals, for apparatuses to synchronize clocks in distant places, such as stations along a railway line. The work was methodical, almost a routine. He had to grasp the essence of an invention, break down its function to fundamental physical principles, and judge whether it was new and feasible. This forced clarity, this reduction of complex ideas to their core, sharpened his thinking in a way no university seminar could have. He learned to separate the wheat from the chaff, the essential from the non-essential. And between the lines of the patent applications, in the diagrams of gears and electrical circuits, he kept finding the same fundamental questions that had occupied him as a boy. What is time? What is space? How does light move? The true significance of this place, however, lay in the freedom it gave him. Unlike the rigid academic world, shaped by hierarchies and conventions, his intellectual work after hours was entirely his own. The 8 hours at the office secured his livelihood and gave his day a structure. But the evenings and nights belonged to his thoughts alone. In his small apartment on Cramgas, often in quiet conversation with his wife Maliva Merrick, herself a brilliant physicist, or in the circle of his closest friends, his mind unfolded. They jokingly called their small, informal circle the Olympia Academy. Together with Conrad Habicht and Maurice Solovine, Einstein would often sit up late into the night. Over simple food, tea, and the smoke from their pipes, they discussed the works of great thinkers, from Spinoza to David Hume to Henri Poincaré. It was a haven of free thought, a place where no question was too bold and no idea too outlandish. Here, In the intimate atmosphere of this self-created academy, Einstein could voice his thought experiments, test them against the critical minds of his friends, and develop them further. It was precisely here, in the interplay between the practical work at the patent office and the philosophical discussions in the evening, that an idea began to germinate that would change everything. The question of clock synchronization from the patent applications would not let him go. How do you ensure that two clocks, one in Bern and one in Geneva, strike at the exact same time? One could send a light signal from Bern when the hand is at 12. But by the time the signal arrives in Geneva, a tiny amount of time has already passed in Bern, the time it took the light to travel. To set the Geneva clock precisely, one would need to know this delay. But to measure the speed of light, you need two precisely synchronized clocks at different locations. A circular argument. Einstein realized the problem ran deeper. It was not a technical inadequacy, but a matter of definition itself. What does a simultaneous mean for two events that occur in different places? He began to suspect that simultaneity could not be an absolute, universal fact, true for all observers equally. It had to be relative, dependent on the state of motion of the one making the measurement. It was a quiet but fundamental tremor in the physical worldview, born from considering a seemingly mundane technical challenge. The invisible seed of a revolution was ripening in the quiet office of a civil servant, whose thoughts were already traveling far beyond the rooftops of Bern, on the paths of light rays through a universe whose rules he was about to rewrite. Chapter 3. The year 1905 began without much fanfare, a year like many others in the heart of old Europe. The gas lamps in Bern cast their warm light on the cobblestones. Carriages rattled over the bridges, and in the patent office on the corner of Speichergasse and Ginfergasse, a young employee went about his daily work. But in the quiet of this office, between examining patent applications for ice machines and writing instruments, one of the greatest eruptions of intellectual creativity in the history of science took place. In a single, breathtaking year, Albert Einstein published 4 papers in the Annalen der Physik, each of which would have been enough to enshrine his name in the history books. 4 sparks of insight that would forever shake the foundations of physics. The first spark concerned the nature of light itself. For nearly a century, science had been convinced that light was a wave, spreading like ripples on a pond. But one puzzle remained unsolved: the photoelectric effect. When light strikes a metal surface, it can knock electrons out of the metal. Strangely, this effect depended not on the brightness of the light, but on its color. Faint violet light could release electrons where even the brightest red light failed. Einstein proposed a radical idea. What if, he asked, light were not a continuous wave, but consisted of individual, discrete packets of energy? He called them light quanta, which we know today as photons. Each packet carries a specific amount of energy, which depends on its frequency or its color. Red light consists of low-energy packets, violet light of high-energy ones. It was like trying to open a coconut with sand. You can pour tons of sand on it, but nothing will happen. A single, well-aimed hammer blow, however, is enough. So it was with light. Only a photon with enough energy could free an electron. With this idea, Einstein laid the cornerstone of quantum mechanics. The second spark illuminated a world even smaller than light quanta. It was about the existence of atoms. Although many scientists already accepted the idea of atoms, there was no direct proof. Einstein found it in a phenomenon that the botanist Robert Brown had observed decades earlier: the trembling, random motion of pollen grains in a drop of water. This Brownian motion seemed chaotic and inexplicable. Einstein, however, realized that it was the result of countless, invisible collisions. The tiny pollen grains were being jostled by the much tinier but tirelessly buzzing water molecules, sometimes from the left, sometimes from the right. He developed a mathematical formula that linked this visible motion to the invisible world of atoms. One could now calculate the size of atoms from the dance of the pollen grains. The invisible had become measurable. The atomic theory was no longer just a hypothesis, but a physical reality. The third spark was the ignition of the real revolution. In his paper on the electrodynamics of moving bodies, he introduced the special theory of relativity, a theory that would forever change the familiar concept of space and time. What this means in concrete terms, what it means when time itself slows down and space contracts, that deserves its own quiet look, which we will turn to shortly. And finally, the fourth spark followed, a short addendum, just 3 pages long, which contained the most famous equation in the world. E equals mc squared. Mass and energy, he realized, are 2 sides of the same coin. A formula of stunning simplicity and of a significance that the world would only begin to grasp decades later. These 4 papers, published within a few months, painted a new picture of the universe, from the tiniest quanta of light to the very structure of space and time. Yet the world took little notice. There were no headlines, no sudden fame. The seeds had been sown, but they lay deep in the soil of academic journals. Only a handful of physicists around the world slowly began to realize that the foundations of their field had been rewritten by a young man in a Swiss patent office. Fame would have to wait. For now, there was the productive silence that precedes the dawn of a new era. Chapter 4. What if a single principle of nature were so fundamental and unshakable that it would force the very pillars of our reality, time and space, to submit to it? From the quiet concentration of the Bern patent office grew just such an idea, a thought of such stunning simplicity and yet such far-reaching consequence that it would remeasure the universe. Einstein started from 2 basic assumptions, 2 postulates that stood like rocks in a stormy sea of physical doubt. The first postulate was familiar and elegant. The laws of physics are the same for all observers, as long as they are moving uniformly. Nothing new here. Galileo knew this already. But the second postulate was the spark that ignited everything. The speed of light in a vacuum is a universal constant. It is the same for every observer, completely independent of how fast the light source or the observer themselves is moving. A beam of light emitted from a speeding spaceship moves at the exact same speed for a stationary observer as a beam of light from a motionless flashlight. This simple fact, which became increasingly clear through experiments like those of Michelson and Morley, contradicted all everyday intuition. And it meant that if the speed of light refuses to adjust, then time and space themselves must change. Imagine a long train moving at high speed through a silent station. In the middle of the train sits a passenger, while a friend stands on the platform watching. At the exact moment the passenger passes the middle of the platform, 2 bolts of lightning strike the front and back ends of the train simultaneously. For the passenger on the train, the flashes of light from the front and back reach his eyes at the same instant. For him, the strikes occurred at the exact same time. But for the friend on the platform, the world looks different. He sees the train moving. The passenger is moving towards the front flash of light and away from the rear one. Therefore, the light from the front flash will have to travel a shorter distance to reach the passenger's eyes than the light from the rear flash. For the observer on the platform, the front lightning strike happened earlier than the rear one. Who is right? Both of them. Simultaneity itself is not absolute, but relative to the observer. This realization leads to a chain of wondrous consequences. If simultaneity is relative, then time itself must also be. A clock that is moving relative to you runs slower from your perspective. You can imagine its hands no longer moving through the clear, thin air of time, but through an invisible, thick honey that slows their progress the faster the clock travels. This effect, time dilation, is imperceptibly small at the speeds of our everyday lives. But as you approach the speed of light, it becomes dramatic. The same is true for space. An object moving past you appears shorter in the direction of motion. 2 trains racing towards a light source would change their apparent length for a stationary observer. The moving train would shorten, as if space itself were being compressed in front of it. This length contraction is not an optical illusion, but a real property of spacetime. And from this new dance of space and time sprang perhaps the most famous equation in all of science. In the quiet of his study, Einstein realized that mass and energy are not separate entities, but two facets of the same coin. He formulated it in an equation of cosmic elegance: E equals mc squared. Energy equals mass times the speed of light squared. Think of this formula not as chalk on a blackboard, but as a glowing jewel floating in the darkness of the cosmos. A silent, pulsating light revealing a fundamental secret of the universe. Since the speed of light is such an unimaginably large number, its square means that even a tiny amount of mass contains a vast amount of energy. A grain of sand holds the power of a thunderstorm. The sun shines not because it is burning, but because it is continuously converting mass into pure energy in its core. The mathematics behind it, which Einstein systematically developed, left no doubt. The special theory of relativity was more than just a new physical theory. It was an earthquake for the human worldview. The familiar, solid stage of the universe, which Newton had built with absolute space and absolute, relentlessly flowing time, shattered. In its place came a four-dimensional fabric, spacetime, in which space and time are inextricably interwoven, able to stretch and shrink depending on motion. Reality was no longer rigid and the same for everyone, but fluid and perspectival. Einstein's work of 1905 had pushed open the door to a new cosmos, but he already sensed that this was only the first step. His theory worked perfectly for uniform motion, but what happened when U included acceleration? What about the ubiquitous, mysterious force of gravity? The silence after the miracle year was filled with new, even deeper questions. Chapter 5. Beyond the miracle year lurked a question that could not be shaken. Special relativity had woven space and time into an inseparable fabric, but it only applied to observers moving at a constant speed. A vast, universal phenomenon was left out: gravitation. Newton's old law described gravity as a mysterious action at a distance, an invisible force that acts instantaneously across infinite distances. If the sun were to suddenly disappear, according to Newton, the planets would leave their orbits in that very same instant. But for Einstein, this was an unbearable thought. Nothing, not even the information about the disappearance of a star, could travel faster than light. Newton's gravity was a ghost in the elegant machinery of his new universe. It did not fit. The solution came to him not in a laboratory, but in a flash of insight he later called the happiest thought of my life. He imagined a man in a closed box, far out in empty space, far from any gravity. If this box were now uniformly accelerated upwards by an external force, the man inside would be pressed against the floor. If he were to drop an apple, it would fall to the floor, just as it does on Earth. The man in the box could perform no experiment to decide whether he was in an accelerating spaceship or if his box was resting quietly on the surface of the Earth. This fundamental indistinguishability of acceleration and gravity he called the equivalence principle. It was the key that unlocked a completely new door to understanding the cosmos. If gravity and acceleration were locally the same, then perhaps gravity was not a force in the conventional sense at all. Perhaps it was something much deeper, a property of space and time themselves. For over 10 years, Einstein wrestled with this idea, filling notebooks with equations, pursuing false leads, and battling his way through the complex mathematics of curved geometry. Slowly, a breathtaking picture began to form. Mass and energy, he realized, warped the four-dimensional fabric of spacetime. Picture a taut, elastic sheet. If you place a heavy ball in the middle, it creates a dent, a curvature. If a smaller ball now rolls nearby, it is not attracted by the large ball, but simply follows the curvature of the sheet created by the large ball. it rolls into the dent. This is precisely what happens in the universe, Einstein proposed. The sun curves the space-time around it, and the Earth, in its orbit, is not following an attractive force, but the straightest possible path, a so-called geodesic, through this curved space-time. Gravity was dethroned as a force and recrowned as geometry. Matter tells space-time how to curve, and curved space-time tells matter how to move. In November 1915, after a grueling intellectual race, he presented his field equations to the Prussian Academy of Sciences, a complex system of 10 differential equations that precisely describes the relationship between the geometry of space-time and the distribution of matter and energy. Such a radical theory had to make testable predictions, and it did. It explained a tiny but persistent anomaly in the orbit of the planet Mercury, a slight rotation of its closest point to the Sun that could not be explained by Newton's laws. It also predicted that light itself must be deflected by gravity. A beam of light from a distant star passing close to the Sun should, in turn, follow the curvature of space-time and be slightly bent. And finally, it predicted the existence of gravitational waves, ripples in space-time itself, emitted by accelerating masses. The boldest of these predictions, the deflection of light, offered an opportunity for verification. One would have to measure the position of stars near the Sun and compare it with their normal position. This was only possible during a total solar eclipse. The British astronomer Arthur Eddington, a Quaker and pacifist who admired Einstein's work, recognized the historic significance of this chance. Amidst the chaos following the First World War, in 1919, he organized 2 expeditions to places where the eclipse of May 29th would be perfectly visible, one to Sobral in Brazil, the other to the island of Principe, off the west coast of Africa. Under the tropical heat and the tense silence of the eclipsed sun, the astronomers aimed their telescopes at the darkened sky. They exposed sensitive photographic plates on which the stars around the black circle of the moon sparkled like tiny diamonds. Months later, after the most careful analysis of the plates back in England, the result was clear. The stars were indeed shifted. Their light rays had been bent by the mass of the sun, and by the exact amount that Einstein had predicted. The news hit like a thunderbolt. The Times of London headlined, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Overnight, Albert Einstein became a celebrity, a symbol of human genius. His intellectual edifice had passed the test of reality. The universe was no longer the rigid stage of Newton's mechanics, but a dynamic, curved entity in which space, time, and matter were bound together in an inseparable, eternal fabric. The door he had pushed open led to a cosmos that was stranger, more beautiful, and far grander than anyone had ever dreamed. Chapter 6. The fame, when it finally came, wore a strange guise. It was not the direct coronation of the intellectual edifice that had reinvented gravity and curved the universe. Instead, the world's recognition knocked on Einstein's door for a work that was nearly 2 decades old, a spark from his miracle year of 1905, the year it all began. In 1921, he was awarded the Nobel Prize in Physics, but in the official citation, one looked in vain for the words theory of relativity. The prize was awarded, according to the committee's cautious wording, for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. It was a pragmatic, almost political decision. The general theory of relativity was still a subject of heated debate, too revolutionary, too difficult to grasp for a unanimous endorsement. The photoelectric effect, however, was undeniable and experimentally confirmed. Einstein's explanation that light is not only a wave but also a stream of particles, quanta, that can knock electrons from a metal surface like tiny projectiles, had opened the way into the quantum world. It was an irony of fate. Einstein received the highest scientific honor for one of the cornerstones of the very theory whose consequences he would struggle with for the rest of his life. With the prize and the confirmation of his general theory of relativity by the 1919 eclipse expedition, Einstein transformed from a respected physicist into a global icon. His face, with its thoughtful eyes and wild hair, became a symbol of genius. He traveled the world, giving lectures to packed halls from Tokyo to New York, and his voice was heard not only on physical matters, but also on political and humanitarian issues. He was the first scientific global star, a beacon of reason in a time marked by the shadows of the First World War. But while the world celebrated him for the revolution he had completed, the next one was already brewing in the quiet circles of physics. A new generation of physicists, led by brilliant minds like Werner Heisenberg, Erwin Schrödinger, and the Danish physicist Niels Bohr, was developing a radically new understanding of matter, quantum mechanics. This theory described the world of atoms with uncanny precision, but the world it revealed was one of probabilities, of uncertainty, and of fundamental randomness. An electron was not in a specific place, but existed as a kind of probability cloud until a measurement forced it to decide. For Einstein, whose entire work was based on the search for a deep, hidden order in the universe, this was an abomination. Thus began a lifelong, friendly, but relentless intellectual dialogue with Niels Bohr. One can imagine the two thinkers strolling through the halls of conferences or sitting in a quiet firelit room. Einstein, who believed in an objective reality independent of us, and Bohr, who argued that reality is only created in the act of measurement. Bohr and his followers formulated the Copenhagen interpretation, which stated that the strange rules of the quantum world were not just a description of our incomplete knowledge, but the fundamental nature of reality itself. Einstein's deepest conviction found its expression in his famous statement, "God does not play dice." He could not and would not accept that the universe, at its core, is governed by pure chance. For him, there had to be a deeper, deterministic level beneath the surface of probabilities, hidden variables that were simply not yet known to us. Quantum mechanics, he was firmly convinced, was a successful but incomplete theory. To prove this incompleteness, he, along with his colleagues Boris Podolsky and Nathan Rosen, devised an ingenious thought experiment that would go down in history as the Einstein-Podolsky-Rosen paradox, or EPR. It was based on a particularly strange quantum phenomenon, entanglement. Imagine two particles that are created together and whose properties are linked. If you measure a property of one particle, say its spin, you instantaneously know, with absolute certainty, the corresponding property of the other, no matter how far away it is, whether in the same room or at the other end of the galaxy. Einstein mockingly called this spooky action at a distance. How could a measurement in one place affect the outcome in another place with no time delay? This seemed to violate the rule he himself had formulated, that no information can travel faster than light. For him, this was the definitive proof that the properties of the particles must have been determined from the very beginning, hidden but real. Quantum mechanics, which could not describe this, had to be incomplete. This debate was more than just a dispute over formulas. It was a struggle for the soul of physics, for the question of what reality even means. Although history would initially seem to prove Bohr right, Einstein's persistent questioning was of incalculable value. He forced the founders of quantum mechanics to sharpen and defend their ideas down to the last detail. This spooky action at a distance, which he saw as a weakness, would decades later prove to be one of the most powerful concepts in modern physics, the basis for quantum computing and cryptography. The dialogue between the two giants remained unresolved, a quiet but persistent intellectual echo that would accompany Einstein to the end of his days. Chapter 7. The wind that blew through the intellectual corridors of Europe began to change. It no longer carried just the scent of old paper from libraries and the quiet murmur of debates, but a cold, cutting sharpness. In Germany, the sky was darkening, and the ideology of National Socialism was casting long, menacing shadows. For Albert Einstein, a man whose entire being was founded on freedom of thought, humanism, and a deep pacifism, this atmosphere became unbearable. As a Jew and as a world-famous free-thinker, he had become not only an intellectual, but also a physical target. His theories were vilified as Jewish physics, his books publicly burned. The world he had understood and helped to shape was turning against him with an ugly, irrational fury. In 1933, while on a trip outside of Germany, he made the difficult but inevitable decision not to return. His home no longer existed. He emigrated to the United States, where he was offered a position at the newly founded Institute for Advanced Study in Princeton, New Jersey. This move was a profound break, a separation from the continent whose scientific tradition had formed him. But it was also an act of self-preservation. Princeton became his new home, a quiet, green enclave of scholarship. Here, in the tranquil small town, he found a refuge. He spent his days walking between his house on Mercer Street and the Institute, lost in thought, a familiar but unapproachable sight, with his disheveled hair and pensive eyes. He found a new intellectual community, though he continued to distance himself from the prevailing currents of physics. While quantum mechanics triumphed, he worked tirelessly and in isolation on his vision of a unified field theory. He sought a single, elegant formula that would unite gravity and electromagnetism, the great forces of the universe, in a single, harmonious description. It was a search for the ultimate order in a world that was sinking ever deeper into chaos. This theory, however, would remain unfinished, a quiet testament to his lifelong dream of a deeper, hidden unity in nature. But the quiet of Princeton was abruptly shattered in 1938. News from Europe reached the physics community that struck like a thunderclap. In Berlin, the chemists Otto Hahn and Fritz Strassmann had discovered something incredible. In an attempt to bombard uranium atoms with neutrons, they had not produced heavier elements as expected, but lighter ones, barium. It was the physicist Lise Meitner who, along with her nephew Otto Frisch in exile in Sweden, recognized the true significance of this discovery. The uranium nucleus had been split. In this process, nuclear fission, a tiny fraction of the nucleus's mass was converted into a tremendous amount of energy, just as Einstein's famous equation E=mc² had predicted. What's more, with each fission, more neutrons were released, which could in turn split other uranium nuclei. The principle of a chain reaction was born, the theoretical possibility of releasing an unimaginable amount of energy in a single instant. This discovery in the hands of Nazi Germany was a terrifying prospect. The Hungarian physicist Szilárd, who had recognized the danger of a nuclear chain reaction years earlier, was alarmed. He knew that only one person had the prestige and authority to awaken the American government, Albert Einstein. In the summer of 1939, Szilárd sought out Einstein at his summer house on Long Island. He explained to him the military implications of nuclear fission and the real danger that German scientists might already be working on developing an atomic bomb. For Einstein, this was a moment of profound moral turmoil. His entire life he had detested war and violence. Now he was being urged to advocate for the development of the most terrible weapon humanity had ever conceived. He looked out at the peaceful landscape before him, but his mind was with the dark clouds gathering over Europe. The danger of Hitler possessing such a weapon seemed to him even greater than the evil of the weapon itself. With a heavy heart, he agreed. He dictated a letter to President Franklin D. Roosevelt, which was signed on August 2, 1939. In sober, clear terms, the Einstein-Szilárd letter warned of the new physical discovery and strongly recommended that the U.S. government begin its own research into nuclear energy. This letter set in motion a chain of events that ultimately led to the Manhattan Project. Einstein himself, due to his pacifist views and German origins, was deemed a security risk and was not directly involved in the development of the bomb. But his signature, the weight of his name, was the crucial spark. The man who had traveled the universe in pure thought had now paved the way into a new, terrifying era of human history, a burden that weighed heavily, and which he would carry with him into the quiet scholarly peace of Princeton. Chapter 8. The last decades of his life were spent in the quiet, academic oasis of Princeton, a harbor of calm after the storms that had swept across Europe. The weight of world history, which he had helped to shape with his letter to Roosevelt, lay heavy on his shoulders, but it did not extinguish the tireless spirit of inquiry that lived within him. In his modest house at 112 Mercer Street, surrounded by books and the soft scratching of his pen on paper, he continued his work. He continued to publish, corresponded with colleagues around the world, and raised his voice, now not only as a scientist, but as the moral conscience of humanity. He warned of the dangers of the nuclear arms race, passionately advocated for civil rights, and spoke out against nationalism and the rigid borders that separate people from one another. When he passed away in April 1955 at the age of 76, it was just as he had wished, in complete quiet. There was no grand public ceremony, no lavish funeral. His ashes were scattered in an unknown location, his brain removed for scientific study, a final, controversial contribution to the science that was his life. He did not want to become a place of pilgrimage, a relic. His legacy was not to be chiseled in stone, but in the ideas he left to the world. And what a legacy it is! His theories of relativity are not just abstract theoretical constructs. They are the foundation upon which our modern understanding of the cosmos rests. Without them, there would be no Big Bang theory in its current, precise form. We would know nothing of the expansion of the universe, of the strange, dark energy that drives it apart. The most bizarre and fascinating objects in the cosmos, black holes, were once just a theoretical curiosity in the equations of his general theory of relativity. Today, we have photographed them. Gravitational waves, tiny ripples in space-time emanating from cosmic cataclysms like the collision of two black holes, were another of his bold predictions. 100 years later, they were directly detected by the LIGO Observatory, a giant laser interferometer, opening up a completely new window to the universe, a universe we can now not only see, but also hear. Even in our daily lives, his legacy is present. Every time you use a GPS system to find your way, you are drawing on Einstein's theories. The satellites orbiting high above us move so fast and are in a much weaker gravitational field that their clocks run differently than ours here on Earth. Without the corrections prescribed by both special and general relativity, the positioning errors would accumulate by many kilometers each day. The system would be useless. Einstein's abstract thoughts on the nature of time and space have become an invisible but indispensable tool of our modern lives. But his legacy extends far beyond physics. He became a global icon, a symbol of something that slumbers deep within us all, pure, childlike curiosity. His face, with its kind eyes, mischievous smile, and famously untamed shock of hair, is known worldwide. It stands for the genius who does not care for conventions, for the mind that dares to ask the most fundamental questions. He showed the world that the greatest breakthroughs arise not from rigid discipline, but from playful imagination and the courage for nonconformist thinking. At the same time, he was a deeply committed humanist and pacifist. He saw science not as an end in itself, but as a means to uplift and unite humanity. He dreamed of a world without war, governed by reason and compassion. His sharpest criticism was aimed at blind nationalism and racial hatred, which he called the measles of mankind. His conviction in the dignity of the individual and the freedom of thought is perhaps more relevant today than ever before. Until his last breath, he worked on a dream that would elude him, the unified field theory. He was convinced that gravity and electromagnetism, the two great forces with which he had wrestled his entire life, must be merely different manifestations of a single, deeper reality. He searched for the one elegant equation that could unite them in a harmonious framework. Although he never found this theory, his quest lives on. Physicists today working on string theory or loop quantum gravity are following the trail he blazed. They are chasing the same dream of unity and simplicity that drove him his entire life. Thus, his story remains an enduring inspiration. It teaches us to look at the world with open eyes, to question established truths, and to never stop asking, why? Albert Einstein encourages us to look beyond the horizon of our daily lives and to recognize the hidden beauty and profound order of the physical laws that govern our wondrous universe. His journey is not yet over. It continues in everyone who looks up at the starry sky and wonders what lies beyond.
That was today's night lesson. Thank you for listening. If you'd like to see more videos like this, please leave a like and subscribe to the channel. Good night and sleep well.